Today we're going to do our first lab of the year, the law of conservation of momentum. You can probably imagine, given the title of this lab, what the problem might be. We're going to try to verify if the law of conservation of momentum is valid. Well, we always want to phrase that in the form of a question. So we're going to say, is the law of conservation of momentum valid for the collision of two dynamics carts? This is a dynamics cart. We're going to collide two of these things together. They're going to stick together during the collision, go off as one, and we want to see if momentum is conserved. In other words, is that law that I've told you about over the last couple of days really true, or are we just making it up? Now, we have to identify some variables, of course. If you think hard enough about this, you might be able to figure these out right away, even without knowing the procedure. Ultimately, if we're trying to verify the law of conservation of momentum, then we're going to compare the initial momentum to the final momentum. Well, what are we going to change here? When we're running this experiment from one trial to the next, what do you think we're going to change from one trial to the next, Matt? We're gonna manipulate it. We're going to change the initial velocity, although that's not our manipulated variable, but it goes really closely along with our manipulated variable. What changes? No. In fact, we're going to keep the mass the same. We're going to keep, listen carefully, we're going to keep the mass the same throughout the entire experiment. So that's not our manipulated variable. We're changing the velocity, and the purpose of changing the velocity is to change the momentum. So we want to manipulate the initial momentum. Now, how do we do that? Well, we do that by changing the velocity, but the actual variable that we're attempting to change would be the initial velocity, the initial momentum, sorry. I won't tell you what the responding variable is, but you can probably figure that out based on what the manipulated variable is, right? If we're changing the initial momentum, then what do you think, don't answer this out loud, what do you think changes in response to the initial momentum? And then, of course, our control variables, everything else has got to remain the same. How are we going to do this? Well, the apparatus you see up on the board here right now, it consists of a triple beam balance scale. The purpose of the triple beam balance scale is to find the mass of both carts. You see two carts up here as well. And I don't know if you can see this very clearly with where you're sitting right now, but on the end of each cart is a little bit of sticky tack. What you want to do is take a little bit of sticky tack, it doesn't matter exactly how much, put it on one end of each cart, weigh the carts. We want to know what the mass of each of these carts is with the sticky tack. The purpose of the sticky tack is so that when we fire or send one cart moving with our hand and it collides with the second cart, it will stick to the second cart. We want that to happen, right? We want to have the first cart going towards the second cart, and then when it hits it, we want the second cart to stick to the first cart and then go off as one object. How are we going to determine what the velocity is? The initial velocity is in the final velocity. Well, we're going to use the motion sensor that you guys used last year in Physics 20 that is connected to the AirLink apparatus by a cord that is connected via Bluetooth to your iPhone. The instructions for using the AirLink are the same as the instructions for last year. I've got little booklets up here that will help you with that. If you refresh your memory as to how to set it up, how to connect it to the motion sensor, how to connect it via Bluetooth to your iPhone, how to download the app on your iPhone, and so on and so on and so on. That shouldn't be a problem. If it is, look in the little booklet, the instruction booklet. If that doesn't help you, then ask me and I can give you a hand with that. So the bottom line is, you're going to set it up the way you see it here. You're going to have cart number 2 at rest. You're going to have cart number 1 at rest, but we're going to send cart number 1 moving with our hand. Okay, we're going to start the process of measuring the velocity with the motion sensor. This motion sensor is going to detect the first cart, the initial velocity of the first cart. It doesn't need to detect the initial velocity of the second cart because it's at rest. When it collides, it's going to detect the final velocity of both of them combined because they're going to have stuck together. If they don't stick together, then throw it at trial. Do another one. One final little thing here before we move on to some of the intricacies of the app here. I mentioned this last year. There's 2 settings on the motion sensor. You got to make sure that you're on the 1 setting. Okay, this little switch goes over here to the cart. That tells you that you're measuring something the velocity of something that's close by and relatively small. If you have it over here, then you're trying to measure the velocity of something big and is walking away from you. You don't want that. Okay, you're trying to measure the velocity of small carts that are close by. So make sure it's on that setting. Probably already is, but if it isn't, make sure that it is. Once you fire up the app, once you've got it all connected here, and you fire it up and you're actually ready to collect data, it's going to be a tiny bit different than last year. Last year, you would see this screen on your phone and you would click on position so that you got a position time graph, a real-time position time graph. That's going to be a little bit different this time around. Today, you're going to click on velocity. Click on velocity, it's going to give you a real-time velocity time graph on your phone. Now, when cart number 1 is going towards cart number 2, then collides with cart number 2, goes off as one object, the graph should look something like this. What does that correspond to? That velocity that you see right here. Yep. Good, the initial velocity of cart number 1. And what does that one correspond to? Yeah, that's going to be the final velocity of both carts. Now, realistically, your data won't look nearly this pretty. Data points are going to be, in some cases, all over the place. Might see something up over here, crazy over there, something over here, whatever. You want to see this shape, more or less, somewhere in the middle of your data. Okay, if you see that shape and you can clearly identify a VI and a VF, then I want you to write down the value of VI and VF. If you can't clearly see that shape somewhere, even if there is a whole bunch of other data that's kind of crazy, measuring before and after the motion sensor was detecting the cart, if you can't see that, then do it again. Delete that data point and do it again. Assuming that you do see that shape, then you're going to record the data on your table. You're going to repeat the experiment, moving the cart at a different speed or a different momentum. Get another set of data for initial and final. Do it again, get another set. Do it again, get another set. I need to record the masses as well, but I only need to record the masses once. Why? They're not changing. So get those values, but they're going to be the same throughout the entire experiment. Once you've got all that data collected, comes time for your analysis. Your analysis includes a graph that you have never seen before. It's a graph of final velocity versus initial velocity. In Physics 20, you learned that the slope of a position time graph was velocity. You learned that the slope of an acceleration time graph was, of a velocity time graph was acceleration. How did you know that? Because your teacher told you. How did your teacher figure it out? Or how did the first person figure it out? Okay, what if we had never seen that graph before? What if your teacher couldn't tell you that the slope of a position time graph was velocity? How would you figure it out for yourself? That's what we're going to learn today. How to analyze a graph that you've never seen before and determine what the slope means on that graph. This is a VF versus VI graph. When you plot that graph on Google Sheets, it should look something like this. It should be a pretty good straight line. You're going to display the equation, which is going to give you the slope. Let's say it's y is equal to 0.55x plus 0.023. The slope of this graph would be 0.55. It's the first number there, right? Y is equal to mx plus b. Now, occasionally, you need to use the value of the y-intercept as well, but in this case, we won't. It'll just be the value of the slope in this case. All right, here's what I want you to do. I want you to come up with an equation that describes this graph. And it's an equation from math class in grade 9 or grade 10. Always the same as long as it's a straight line graph. From your graph, the equation will always be, for every straight line, y is equal to mx plus b. But what we want to do with this equation is tailor it to this specific graph. So in other words, instead of just calling it y and x, we're going to call it VF because it's VF on the y-axis. We're going to replace the letter M, by the way, with the word slope. I don't like using the term M for slope because I find what often happens is we get it mixed up with mass. So call it the word slope, and then we're not going to get it mixed up. X is going to be V1I. And in some cases, there will be a y-intercept, but in this graph, your y-intercept will be so small, or 0, so small that it doesn't matter. It's effectively 0. So y is equal to mx becomes vf is equal to the slope times vi. Then you've got to get an equation either from your data sheet or derive an equation or some equation that you've learned about that isn't on your data sheet that is relevant to the concept that we're talking about, but also has these variables in it. I'm going to say pi equals pf, and then I'm going to say m1 v1i plus 0, because the second object is at rest, right? It has no momentum, equals m total times vf. The total mass of cart 1 and 2 combined, because they stick together, times the final velocity. That's an equation that's clearly relevant here. We're talking about a collision, but it's also got the same two variables in it, vf and v1i. Let's rearrange the green one here to look more similar or look closer to the one that's in blue here. vf equals m1 over mass total times v1i. Now we've done all the legwork. We've done the hard work here. Now comes the easy part that leads you to a conclusion. I want you to cross off variables that appear in both. VF appears in both. VI appears in both. What are we left with? Slope and M1 over MT. That means the slope of this graph is equal to mass 1 over the total mass. We could have easily went through that analysis last year for position time graphs, but we didn't need to. We weren't at that point yet at the beginning of Physics 20 where we could go through this, I suppose. Now we could. Now we could figure out that the slope of a position time graph is velocity using this method, but we already know that. Now we know the slope of a velocity versus velocity graph is mass 1 over mass total. So here's what you got to do. Get the slope from Google Sheets. In this case, 0.55 or whatever Google Sheets spits out for you. Divide mass 1 by mass total. You measure the masses, right? So physically calculate that value. And then I want you to compare. So the slope should be equal to m1 over mt. Is it equal to m1 over mt? Get the slope from the graph, get m1 over mt from your data, and then compare those two values. Here's how you draw your conclusion. If those two values are the same, then the law of conservation of momentum must be valid. Why? Because we made an assumption here. Look at the assumption we made. We assumed pi equals pf. We assumed the law of conservation of momentum is valid. If these two numbers equal each other, then the assumption that we made must be correct. Does that make sense? We would have gotten a completely different number for m1 over mt compared to the slope if the assumption that we made was wrong. So compare those two numbers. If they're the same, then the law of conservation of momentum holds. If they're different, then it doesn't hold. Well, how close do you got to be? Let's calculate a percent difference. You guys remember the equation for that? Actual minus theoretical over theoretical. The actual value here will end up being the slope. The theoretical value, what it should be, is m1 over mt. Actual minus theoretical over theoretical. times 100. You want to be within 10%. So if your percent difference is less than 10, you can safely conclude that the law of conservation of momentum is valid. If it's greater than 10%, then you would say the law of conservation of momentum is not valid in this situation. Of course, we know that it should be, right? If it's not valid, then there's got to be some sources of error that tell us why it's not, why it wasn't verified. But if it's greater than 10%, I want you still to say that it's not conserved. You need a conclusion. Was it verified? Yes or no? How do you know? How do you know relates to what we just did, right? You don't have to provide the details of what we just did in your conclusion, but briefly explain the mathematical analysis that you did to determine whether it's valid or not. And then finally, of course, you need sources of error. Maybe 3 good sources of error and then suggestions for improvement. The following is not a good example of a source of error. We made a calculation mistake. The following is not a good source of error. We measured it wrong. Okay, those are human errors. We don't want those. Okay, if you made human errors, then fix it. Be more careful. We're looking for things with your procedure. Maybe the procedure could have been a bit better. Things with your materials. Maybe this could have been a little bit better. Things with your time management and so on and so on. But not human errors. Not mess ups that you did. Okay. What do you got to hand in? The problem that I already gave you. The variables. I'm not going to make you do a hypothesis, materials, or procedure. Data comes next. Analysis. Conclusion. And sources of error.